Hello everybody, welcome to the latest B-Team live stream. Oh, that rhymes, we should start using that, B-Team live stream. Today we're going to be looking into thinking about how we improve the design of the Tangle, because so far B has obviously been a very experimental project, and in order to make sure things are built in a timely manner and so on, we've been implementing things in a relatively naive way, not sort of an explicitly bad way, but we've not been overly optimizing at an early stage, because that's often not particularly wise to do if you don't properly understand all of the access patterns that you're going to be encountering in a particular project. And often it's the case that it's useful to create a prototype first, do a bit of benchmarking, work out exactly what needs doing and where, and how you're going to access certain kinds of data and how data is going to be moved around, and then you can optimize a new design around that. So just as an initial check, hopefully my audio is working well. Could someone confirm in the chat, or hopefully say no, we can't hear you if you can't hear me. Okay, that's good. Sounds like it works. So next thing, I hope you don't mind, I'm going to be drinking some tea from time to time. I hope it's not too loud on the mic. So first things first, the Tangle is the I guess you might say the primary data structure within the B node. It describes the relationship between messages in the network. So of course, the Tangle is DAG, directed acyclic graph, which means that each node can refer to previously existing nodes in the Tangle. And this means that you can't get cycles in the Tangle, which means that you can perform certain kinds of operations on it, usually things like walking the Tangle and visiting nodes and so on, without basically needing to remember where you've been in order to prevent loops. This is quite useful. You see this kind of data structure not a lot, but quite frequently when programming. So we're going to be starting to come up with a design that improves those kind of data access patterns that we come across a lot within the B project. So currently our Tangle is pretty much just a glorified hash table or hash map. So the way this works is that every entry in the table is mapped from a key value to the value itself, and you can access a value using its key and you get the value back. So this is a pretty fundamental data structure when you're writing code. I'd argue it's pretty much the second most used data structure beyond something like a vector. When you start to learn programming, you're often taught things like doubly linked lists and so on, and skip lists and all of that. But it turns out that excuse me, that a hash map is by far and away probably the most common data structure that you'll be using. They're quite good at a lot of things. They have what's called constant access time, which means that no matter how large you grow your hash table, the time to access any given item in the hash table using its key will always be a constant time. This is quite a useful property. I say constant time. In practice, that often depends on a lot of other factors that I won't go into here. However, that constant time is not necessarily small, because the way a hash table works is that it takes the key value and it performs a hashing operation on it. So a hashing operation something like MD5 or SHA-3 or something. I'm sure you're aware of hashing operations. We don't use any of those because they're not particularly suited to this. We're not looking for a cryptographic hash. We're just looking for one that allows us to place data in the Tangle in a certain way. In some cases, we might be looking for a cryptographic hash because often you can use that as an attack vector for something like a DOS attack. But in the way we're currently using it, that's not too relevant. But you take the hash of your key and you use it to calculate effectively a pseudo-random number. And then you take the size of your hash table and you modulo this pseudo-random number according to the size of the hash table. And this gives you your index. There's a little bit more to it than that because, of course, hash conflicts are pretty common, especially when your table is quite small. And so you have to have an algorithm for working around that and managing conflicts and making sure that two items don't occupy the same slot. But this is why it's got a constant access, because you can always calculate the appropriate place to find your value just from your key itself. You don't need to inspect any of the other elements, sort of. So this has been working fine so far, but it has some teething issues that we'd like to address. So one of these is that when you're inserting items into the hash map, I lost my train of thought. Yeah, when you're inserting items into the hash map, there's the potential need to grow the hash map if it's too small, or shrink the hash map if it's too small and you're removing an item. And this is not great because it involves moving the location of all of the hash map items in memory. So why wouldn't you want to do that? Well, there's a variety of reasons, and the first one is that it's slow to move things around in memory. It's not that slow, but it's slow enough that you want to avoid doing it where possible, but it might not always be possible to avoid that. The next problem is that moving things in memory is effectively mutating the Tangle. It's changing its state in a way that other threads trying to access the hash map might not be able to account for. So you have two threads. One is attempting to fetch a value from the Tangle. One is attempting to insert a value. Then a reallocation that involves moving memory around in the middle of that will mean that your reading thread will have a broken view of the Tangle, right? And in languages like C and C++, this would be effectively a race condition, okay, and it could lead to undefined behavior. In fact, it arguably is undefined behavior on itself. So you don't want to be having that, and so a necessary thing to do is to protect the Tangle somehow, that the access patterns to it don't allow two threads to get an inconsistent view of the Tangle at any time. So a common way to do this is using a mutex. So a mutex is effectively a lock, a concurrency lock, that prevents more than one thread going into it at the same time. And this works great because it means that multiple threads can't get an inconsistent view of the Tangle. The problem, of course, is that it's quite a bottleneck. You have your mutex only allows a single thread in at once, which means if you have 20 threads attempting to all access the Tangle because they're all trying to perform a node sync or something, or they're trying to perform some kind of Tangle walk, then you're going to have a bit of a problem there because they're all going to stop each other going in. It's the equivalent of trying to create a train station where the escalator can only allow a single person in. I mean, of course, that applies to a lot of train stations, but a common thing is to build multiple escalators, right? And that increases your throughput, and the same applies here. Excuse me. So another option that's a little better is an improvement on the mutex design, and this is called a reader-writer lock. And this is a kind of lock that allows many reading threads into the Tangle, because reading threads aren't going to be mutating the Tangle, and so they can't interact with one another, which means that they're not going to get an inconsistent view of the Tangle. Or instead of many reading threads, it allows a single writing thread. So this is a bit better, because most operations on the Tangle are reading operations. Insertion is not rare, but rarer than a reading operation. This means that most threads can concurrently access the Tangle, and this is great. This works quite well. Shared data structures are generally a good thing, but it too has its issues. So one of these issues is that lost my train of thought again. Yeah, one of these issues is that if a thread wants to perform a write, it's got to wait until all of the other reading threads are done. So this is often known as writer starvation, and writer starvation can be a big problem with reader-writer locks. And it means that the potential tail latencies, as they're called, for a writing thread are potentially very, very high. So a tail latency is like a worst case latency. So if all of the stars align and all of your reader threads are in exactly the wrong place, your writing thread can be waiting for a very, very long time for all of the reading threads to stop doing their work. And this is a big problem, okay, because insertion is a necessary operation when you're doing something like a Tangle sync. You don't want to be staffing your synchronization while you're doing loads of other reading operations. So there are a few ways around this, and one of them is to adjust your reader-writer lock so that it's what's called write preferring. And a write preferring reader-writer lock is one that when a writing thread signals that it wants to start accessing the Tangle, it will automatically be bumped up in the queue. So it will become the first priority to gain access to the data structure afterwards. It's still got to wait for all of the other current reading threads to stop doing their work, but after the current ones are done, it can immediately start going. And this significantly reduces the tail latencies, but it also hurts reader performance. So there's a bit of a compromise here. It's usually a worthwhile compromise in most cases, but it's not necessarily something you want to do all the time. So this is effectively where we're at with the current Tangle. Excuse me. It's basically a write preferring reader-writer lock that protects a hash map. There's a bit more to it than that. I'm not going to go into all of the details because we'd be here probably for the entire live stream. But the gist of it is that we want to move away from this design in favor of a design that can allow both readers and writers to access the Tangle at once, and potentially even multiple writers at once. So there are a few ways of doing this. There are certain algorithms that can operate on hash maps or hash map-like data structures in a concurrent way. There's actually still quite a lot of research going on in this area. surprisingly, it's very far from being a solved problem. And the current best-in-class attempts are usually quite hard to verify, and they can come with their own downsides in a lot of other ways. So we are quite lucky with the Tangle because the Tangle has certain properties that we can optimize for. So one of the properties is that it's insert only. So once you've inserted an item into the Tangle, it never goes away. It can go away in certain cases. This is called pruning, but it's not particularly relevant for this case at the moment. In general, once you've inserted, you don't really need to remove. So that's quite a useful property, and you can take advantage of that in several ways that I'm going to discuss later. A few other things as well. So I've discussed how we would preferably want multiple tasks to be able to write to the Tangle at once. And there are quite a few ways of doing this, but a really common one that you tend to see, and actually a pretty good one, is called sharding. And sharding is where you take a data structure that is not normally thread safe, you replicate it effectively into multiple shards, and then you break up your operations between those shards and protect each of those shards in turn, okay? It's not possible for all data structures. For example, you can't really do this with linked lists, at least not in a particularly useful way, but you can do it with a hash map. And the reason for this, as mentioned previously, is that you always know where your item is going to be roughly based on its key and the hash of that key, okay? So this is quite useful. One moment. So keys and hashes. Yeah, okay. So one technique you can do is to first deterministically choose a particular shard to use for your item based on the hash of that key. So just like previously, where you calculated a hash and then you modulate it around the size of the hash map, and then use that to find an index, what you can do is you can take that same hash and you can modulate it around the number of shards and use that to choose a particular shard to use. So effectively, you might have, say, 20 to 30 hash maps, all effectively sitting in parallel, in such a way that you can read and write to each of them in turn. So this does not guarantee that a writer will never be blocked by another writer, okay? Because if you have two keys, or rather two items that are trying to be inserted, and both of their keys have a hash that points to the same shard, then they're both going to be trying to access the same shard at once. And this is a thing that you can't do, basically, because of the problems I mentioned previously. And so you've got to lock each shard, okay? But it does dramatically reduce the chance of two writer threads getting stuck trying to access part of the Tangle. Sharding is a fairly naive technique, and there are better techniques for certain cases, but it's also one that's really quite easy to verify as correct. It's quite easy to do in a safe manner, and it still gives you a pretty considerable amount of the scalability that more complicated techniques provide. So sharding is probably going to be the basis for the Tangle rework, at least in part. There are some extra things to mention on top of that I may or may not get to in this session. So another feature that is important to realize with the current implementation of the Tangle is that when we insert items into the Tangle, those items get sent off to the database for storage. And this is quite an important stage, because it means that if the node dies, if the node loses power or something, or you just close the node down, you don't need to repull all the Tangle history from the network when you restart it, because that would be extremely slow and not particularly practical. So instead, you can just access it from the database. But of course, this means you have two kinds of state. Okay, you have the state that's in the database and the state that's in the Tangle in memory, and you want to keep these two things in sync. So one of the major factors is that the Tangle itself is responsible for transparently maintaining and synchronizing this data between the database and the in-memory Tangle. So we implement this as basically a transparent cache. A transparent cache is a cache where you don't know that you're using a cache. So for example, when you load up your favorite website, be it YouTube or something, your browser is going to start to fetch assets from the web, right? But if you've been to that site previously, your browser probably has them in cache. It probably has them stored away in a cache location on the file system, in which case it can just take the data from the file system. It can make sure that that data is no longer invalidated just by maybe comparing a hash, and then it can provide that data. And you as a user are completely indifferent to this. You have no idea it's happening, and the only perceptible difference to you is that your web page loads faster. Transparent caches are really great because they mean that nothing above it in the tech stack needs to care that there's a cache there. So this is what we want to do with the Tangle. We want to effectively allow the Tangle to pretend that it's larger than the memory of the machine it's being run on. So that's another responsibility of the Tangle that we've got to manage. There are also a few other bits and pieces that we need to manage as well, like milestone information and also the updating of message metadata, including various flags like solidification state and so on. So although the Tangle is an insert only data structure, and although it is supposedly completely immutable, in practice there are certain kinds of data that we do need to update in the Tangle, so we can't just go for a completely immutable data structure. Right now I've been talking for 25 minutes without so much as typing a single character. So what I've done here is I've created a new crate within the B project, and I called it Tangle 2. So in practice, we're probably going to be transplanting a lot of the code over from the old Tangle because a lot of it is very useful. But when we're designing all of the core stuff, it's quite useful to start in another part of the repository, and then you don't have to move around inside the existing code base and deal with naming conflicts and all of that. You can just move it over as and when you're ready. Right. So the first step is that we want to make sure that we can have an API for the Tangle that's going to be pleasant to use. So you may think, oh, well, the Tangle is just an internal component. It's okay to be complicated and so on. But I don't think that's always the case. I think it's really important when you're writing code to produce clean and efficient APIs. And ideally, where you can, it's important to create APIs that are very difficult to use incorrectly. So a good example of this is a lot of the abstractions that Rust has got in the standard library. If you use a mutex in C++, a mutex only acts as a block for flow control. It doesn't actually protect any particular data. Compare it to a mutex in Rust, where the mutex itself will wrap the data and it will prevent access to the data without first making sure the mutex is locked, which guarantees that the API is safe. So there's basically no way to abuse this without explicitly opting in to using unsafe code. And there's no point in doing that really, because the mutex works fine in safe mode. There's no overhead to it at all. But what it does mean is that the compiler can statically verify the code that you've written, and also you as a programmer can be confident that it's not going to break, that it's not going to access undefined memory, that it's not going to do all kinds of other nasty things that code can do. So I'm going to start off creating a Tangle struct. So we're doing a bit of Tangle 101 here. We're starting afresh and coming up with an API that we think is going to be useful. So one of the useful things with concurrent data structures is that when you have a data structure that runs on a single thread, every operation you apply to it is immediately applied. Oh, my tea's getting cold, which is a catastrophe. Every single operation you apply to it is immediately applied. So if you, let's say I'm going to do an example down here. If you have your hash map called myMap, and then you insert it with a key and a value, when you do something like mymap.getKey, straight afterwards, you can be certain that that value you're going to get back is the one you just inserted, okay? That means that there is a strict one-to-one linear relationship between the operations you perform and the ones you get out of the data structure afterwards. With concurrent data structures, that's a lot harder to enforce unless you're very careful. So a big factor here is, let's say you had this code again, and instead your data structure is basically just a hash map but protected by a mutex, for example. You might perform an insertion here, and you might try to get the result, and you might end up with an error here. And the reason for that might be that elsewhere in another thread, you have another thread that's trying to remove that item as well. And so what you end up with is this state where you can't guarantee that every subsequent operation on the data structure is actually going to be consistent unless you maintain a lock of the data structure between them. And this is a bit of a problem actually, because a lot of algorithms rely on this kind of consistency. So there are certain advantages that the Tangle has here. So for example, when we insert a message, we know that the message isn't going to just vanish because there is no Tangle remove message function. It just doesn't exist. But there are other factors. For example, when the Tangle in memory gets too large, it grows too big, and we start using too much memory, we have to evict entries out of it. Okay, and this means that when we evict these entries, we effectively have to remove them, but they still remain in the database itself. So if the Tangle performs a get here, and in this space the entry has been evicted out of memory, then this get is going to have to perform an access to the database, which is not ideal. We want to avoid that. So we use something called an LRU cache. So LRU means least recently used. And the idea here is that whenever you perform an insertion, or you perform a get, or you perform really any kind of access to a particular key or a particular message in this case, that message effectively goes to the top of the queue when it comes to eviction. So you pull things out of the bottom of the queue, and this makes sure that you're not going to be evicting an entry that's really recently been used by a particular service. And this means that your average access times are going to go down, because if a particular user of the Tangle is trying to access a particular message, there's a high likelihood that it's going to be trying to access the same message again in a short while, because maybe it's very recent on the Tangle, it needs a particular lot of analysis or something like that. So this LRU cache effectively is a way to balance average access times against the fact that memory is inherently limited. So there's a little trick that we can use here, okay? So the problem here was that there was no consistency between this insert and this get, okay? But there's a difference between something called total consistency or global consistency and local consistency. So when you perform an insert, you want any subsequent get to work fine. But if you were to perform that insert on another thread, you might be okay with that being invalidated, okay? So the only guarantee really is that any one thread must have a consistent view of the Tangle, but each thread could itself have a slightly different view of the Tangle. This kind of design actually has quite a lot of advantages, because it allows you to make a data structure more concurrent, more able to be spread across threads, because you can cache particular changes on the side of a thread, or you can put them in something like a queue to be changed later. So the way that we might want to do this is we might want to come up with a kind of abstraction that defines a single thread. So that's quite hard to do, because you could be accessing the Tangle from anywhere and you don't know what thread is accessing it when, and so you don't know which calls need to be consistent with one another, okay? Excuse me. Right, so these calls need to be consistent with one another on a single thread, but you don't know which ones need to be consistent. So one way you might do this, or at least the Rust way, is to add another type, right? Rust absolutely loves types. Types are all over Rust code, and I love types and I think they're great. Types are a good abstraction and they should be used more in the software industry. So a type you might use is something like a Tangle handle. So this might represent one logically consistent access to the Tangle. So instead of accessing it via my map, you might do something like you might create a handle from the map and then use the map to perform insertions and gets. And because this is a distinct type, we can make sure within the type that all subsequent inserts and gets are self-consistent. And this is quite useful because that means your algorithm that uses this handle is going to have a consistent view of things, while at the same time that data might not yet get propagated back to the main Tangle. So this means effectively that the views of the Tangle from different threads may be different, but provided you're using the same handle, they will be consistent. So this is quite useful. So for now, let's get rid of this example code here because it's no longer relevant. We might implement a method on the Tangle that gets a handle. So this function, or this method rather, is going to give us back a handle. So one thing we want to make sure is that this handle isn't going to outlive the Tangle itself. So the Tangle has only got a limited lifetime. It will be created when the node starts, and then as part of the shutdown process, it will also be dropped. It will also be destroyed again. And that's fine. That's a perfectly normal part of the way programs continue executing. But an important part of this is making sure that this handle doesn't outlive the Tangle, because if it does, we can continue calling methods on this handle, only for them to have absolutely no effect. So a way we might want to deal with this is to use a special Rust feature called lifetimes. So lifetimes allow you to guarantee that there's a relationship between two particular pieces of data that guarantees that one will always outlive the other. So you do this by declaring a lifetime, kind of like a type parameter. In this case, what we would normally do is we parameterize this function with a new lifetime that basically says our resulting Tangle handle has got the same lifetime as the lifetime we access the Tangle with, which means the Tangle cannot be outlived by our Tangle handle. Now, this is quite a common pattern in the Rust ecosystem, so they came up with a way of making this basically completely implicit. So you can just completely elide the lifetime here, and it will automatically infer it as such. So let's create our Tangle handle here. And what we're going to give it is we're going to give it a reference back to the Tangle. So what we can do now is let's create an example function. How are we going to do this? Let me just check. Actually get rid of those now. Okay, let's create a new test function. So this test function is going to create a new Tangle. Then it's going to create a handle from it. And then what we're going to do is we're going to check the lifetime relationship by first dropping the Tangle, then only afterwards we're going to drop the handle. So this shouldn't be allowed. We shouldn't be able to drop the Tangle prior to dropping the handle. We also need to implement this default method. There's a way to do that by just deriving default. So now we're going to run cargo test just to make sure this this doesn't compile, basically. There we go. Taking its time. We've got a lot of dependencies because I just duplicated the old Tangle crate and removed all of the code, so all of the old dependencies are still there. Actually, I might get rid of them. Yeah, we don't need any of them. So we kind of reduced them. There we go. Okay, so we've got basically no dependencies now. And you can see Rust is giving an error, as it should do, basically saying that the handle itself borrows the Tangle, and because of that, the handle can't outlive the Tangle. So if we switch this ordering around, we get no error. It works. So that's good. Rust is enforcing this particular data relationship for us, and making sure that this code will be 100% memory safe. It won't be able to trigger undefined behavior. That's not to say it can't trigger strange or unintended behavior. It can't trigger non-local behaviors that could be security risks or something like that. So the next thing to do is we're going to want to create a sharded map effectively within the Tangle. I'm probably not going to do this in this live stream because there's only about a quarter of an hour left, and I've kind of already done it for the existing Tangle, although it needs a lot of improving. So what I'm just going to do is I'm going to just define a struct up here. I'm going to import that's going to be S hash map, which just means sharded hash map. It's going to take a key and a value, and then we're just going to use the phantom data type just to pretend to Rust that we're doing something clever with it, even though we're not. So now we can do then our key value is going to be message ID, and the value is message. So for this we're going to need actually we're going to need b message in the dependency tree. So right. So the next thing that we're going to want to think about, this may take some time. I said that each subsequent call via a particular Tangle handle needs to be self-consistent. So there is actually a really nice way of doing this. And this is to have the handle itself keep a record of all of the insertions we perform. And then we can have those insertions wait until later, until they actually get propagated to the main Tangle. So what we can do is we can have another task in the background, a background task that is taking our Tangle data that we've declared in the handle. It's queuing it all up, and then it's applying it when it gets the chance to do so. The reason we'd want to do that is because it means that every mutating call via the Tangle handle is effectively what's called non-blocking. So because it's all queued up, we don't have to okay, well, that needs to be done. 1O. Okay, cool. So because we're queuing up all of these insertion operations, this allows us to not have to wait for any other threads to perform these insertions, okay? Because the background worker will get to it when it gets to it, and when it gets to it, it will perform the insertion, of course. But that means that data may take some time to propagate between threads, but that's okay because we've already said that we only care about having a consistent view of the Tangle when using the same handle. We don't care about the Tangle overall having that view of things. Excuse me. Next thing. I did have a bit of an itinerary for this, but I didn't have much time to properly plan it out. I was working on other things. So, yeah, as I say, this sharded hash map can eventually be implemented, but for every handle, we're going to want effectively a hash map of changes that we've made to the Tangle. So these are not, this is not the same as the Tangle itself, but effectively we want to list all of the changes that we've made to this to the Tangle via the handle. And when we access the Tangle handle, we're going to first check the changes to make sure if there's anything that's previously been changed, and if so, we can just use that data rather than invoking the main Tangle. So I'm just going to use a normal hash map here because our Tangle handle is only going to be used from a single task. So we don't need to protect it with locks or anything because we're not going to have multiple threads attempting to access it. And this is the big advantage of this pattern, right? You effectively turn a concurrent data structure where lots of threads are trying to step on each other's toes and try to wait for each other into a single threaded data structure where changes are eventually propagated back to the main data structure. Just going to create a hash map here. So our key is going to be message ID because these are changes we make to messages, and our value is going to be this change data type, and the change is going to be something like this. So one thing we might want to do is we might want to insert the message outright. Okay. So think for a moment. Okay, so message insertion is going to involve our message data that we just inserted. I'm going to put the message ID in here. We wouldn't normally need that because the message ID is also here and we're already using it to access the change. However, I'd like to use this data structure as part of a queue of changes that get propagated to the main Tangle as well. So I'm going to leave that in there for now, and I'm sure it can be changed later. The edges can be optimized and so on, but right now I'm not interested in optimizing every single last piece of code. I'm interested in getting the broad strokes of the design correct. So we might want to insert a message. We probably don't want to we probably don't want to remove them because the Tangle, as I mentioned, is an insert-only data structure. Okay, but we might want to modify the Tangle in some way. So, for example, we might want to update part of its metadata. So this is a little bit out of the scope of this live stream, but along with a message body, each message has also got a little piece of metadata, and this metadata gives the node various information about the message and things like whether the message has been confirmed by other messages, and this gives us a bit more information about how to deal with it and when it can be used in certain cases and so on. For now, I'm probably just going to treat that as a separate struct which contains nothing. But yeah, this is one thing we want to do. So insertion also includes inserting the metadata. But an update to the metadata might look like this. We might have the message ID that we're updating the metadata of and the metadata itself that's being updated. I think in practice there's going to be a bit more to it than this, because certain operations we don't want them to conflict. For example, we don't want two Tangle handles that try to apply different kinds of data to the Tangle that are conflicting, because one might effectively overwrite the other. So for certain things, we can guarantee that once a piece of data is changed, it will stay changed. For example, when a message is confirmed, it will stay confirmed. In which case, we can apply an operation like a logical OR operation to the metadata, and then take the union of the existing Tangle messages metadata and the new metadata that we're getting from our Tangle handle. But I'll probably deal with that later, because with 5 minutes left, there's not too much to say on that that's going to really be particularly interesting. There are more changes as well. Since this stream is a bit ad hoc, I'm probably not going to go into them right now, but hopefully you can see the broad strokes of the new design that we're going for. We use this Tangle handle abstraction to make sure that all modifications to the Tangle are non-blocking, and that all operations on the Tangle are consistent and provide the same data back. There is one other thing I'll probably implement before time is up, and that's that there's more to storing information about a particular message than just the message data itself, right? The lack of existence of a message is also useful information. So knowing that we don't currently have a particular message present in the Tangle also gives us information about things we can do or things we can't do. So for example, if we don't have particular information about a message, we might want to request it from our peers in the network. So one way to do that is to switch this data type to an optional data type. So an option can be either containing this data or it doesn't contain this data. It's basically like a nullable type in other languages. And this gives us a lot more useful information. For example, it means that if we perform a query on the Tangle asking whether a particular message exists, we don't have to query the database if we ask that question again a second time, because we already have in the in-memory cache the information that no, the message does not exist. Okay, so this is quite important because this means we don't do unnecessary work asking the database for information that we should really already have access to, but we just don't. And this is a feature we don't yet have in the current Tangle implementation. And I think it's actually going to be quite useful. And will probably come with a fairly significant performance improvement. The font is too small. Sorry about that. I hope it's hopefully visible. At least it seems to be when I'm viewing the video, but I understand that not everybody's eyesight is the same, so apologies for that. Yeah, I think that covers the general gist of what I wanted to explain in this live stream about the new design. I'm not going to go into the exact implementation of it because it's no doubt going to be rather complicated and take some time to get right. And most of it isn't particularly interesting anyway. It's small sort of things like making sure that race conditions don't occur in certain cases and stuff like that. Yeah, so this is just an evolution of the existing design. I think time is pretty much up. There's 3 minutes left, so if anybody has any questions, feel free to ask them. I'm very happy to answer to the best of my knowledge. I'll give it a few minutes for questions to come in. Quite sad actually. I only got about 2/3 of the way through my mug of tea before it was too cold to drink. I was talking too much. Might have to brew some more. So I see no questions yet, so I assume there's nothing. How long have we got? 2 minutes. Excuse me. Yeah, I don't think there's really that much more to talk about within this live stream. Does anyone else have anything to add, Thibaut or Alex, or are you all good? Okay. In that case, we're pretty much a minute away now, so I'll say goodbye and join us for the next one, which will probably be next week, assuming everything goes to plan. See you later.